Geometry 1. In this video we're going to take a look at converting from degrees to radians and back from radians to degrees. Then we'll take a look at Pythagoras Theorem and what sine, cosine and tangent mean with regard to a right angled triangle. We can see three different types of angles here. So the top left-hand angle is called an acute angle, and that's where the measurement of the angle theta lies between 0 and 90 degrees. The second angle, where theta, the angle, is 90 degrees, is called a right angle. And the third type we're looking at in this course is an obtuse angle. So in an obtuse angle, the angle theta lies between 90 and 180 degrees. Angles can be measured in degrees or in radians, and the measure of a radian is such that if I have a circle, if you see the circle on the left here, and the radius of this circle equals r, if I extend an angle, the distance of r, along the circumference of this circle, well, then the angle extended will be 1 radian. So the angle theta is 1 radian. 180 degrees equals pi radians, and there are 2 pi radians in any one circle. So we'll do some examples now of converting degrees to radians. So if I want to convert a degrees to radians, so we'll take my degrees and we'll multiply it by pi over 180. And that will cancel out the degrees and give our angle as a measure of radians. So the first example would be, look at 90 degrees. So 90 degrees times pi divided by 180. And the 90 over 180 gives me 1 over 2 equals pi over 2. So we've converted 90 degrees to radians. We could also do, say, 45 degrees. 45 degrees times pi over 180 will give us pi over 4 radians. And these are measured now radians. We don't always have to express it in terms of multiples of pi, where it's quite common to have them as multiples of pi for angles such as 30 degrees times pi over 180 is pi over 6. 60 degrees times pi over 180 is pi over 3. So there are common angles that we'll always express in terms of pi, but if I was converting something like 36 degrees times pi over 180, I'll take the calculator up. The calculator can show it as a multiple of, so we're looking at 36 degrees, so let's say 36 times, and we'll find the pi as shift, and we divide that by 180. So we have actually in this instance, we have a multiple 1 over 5 times pi. We can also express that as a decimal quantity. We can decimalize that to show it as 0.6283 radians. And that is the same quantity, albeit rounded to 4 decimal places. We can also convert back from radians to degrees. So radians to degrees. So again, we will do the reverse operation. So if maybe I'll say 2 pi over 3 radians. To convert this to degrees, we'll times 180 over pi. So when we do that times 180 over pi, we'll do that one on the calculator. So we had 2 over 3 pi times 180 over pi. And that gives us 120 degrees. And we could do maybe, if we did 3 over 2 pi radians times 180 over pi, we get 270 degrees. You can check that on your calculator. Again, our radians can be given as decimal figures. So, for example, 0.653 radians. Converting 2 degrees, we multiply by 180 over pi and calculate. So 0.653 times 180, and that will be over pi, and that equals 37.414 degrees. We'll take a look at Pythagoras' theorem now, which most people should have done in high school. It relates to a right angle triangle, and here we can see the right angle is at angle C, and the length opposite the right angle is always the longest length in a right angle triangle. So small c is the longest length. A is the angle, capital A is the angle, small a is the length opposite A. Capital B is the angle at the top, and small b is opposite. So Pythagoras' theorem says that the length c squared equals a squared plus b squared. Or otherwise stated, the square of the hypotenuse equals the sum of the squares on the other two sides. So the hypotenuse is the longest length in any right angle triangle. And we can use this when we know two lengths and we're looking for a third length. So the first example, we can see the right angle triangle, and in the example 13 we can see is the hypotenuse, and we have the length 12 and we're looking to find x. So if we plug that into the Pythagoras theorem, we'll say 13 squared equals 12 squared plus x squared, and then we'll rearrange it to find we've got x squared equals 13 squared minus 12 squared, and we'll end up with x equals the square root, and that would be the square root of 25, x equals 5. In the second example, we could see the right angle triangle. The second example, the hypotenuse this time is 5. We have a length measuring 3 units, and we're trying to find x. So in this example, we have 5 squared equals 3 squared plus x squared. We can rearrange that. X squared equals 5 squared minus 3 squared. X equals the square root of 25 minus 9 is the square root of 16. X equals 4. In a right angle triangle, the length that's opposite the right angle is always known as the hypotenuse and is the longest length. If we're interested in the angle theta, well then theta can be given by sine theta equals opposite over hypotenuse. We could say cosine theta is the adjacent over hypotenuse, and the adjacent means the length beside the angle we're interested in. And then tan theta is always sine theta over cosine theta. So sine, cosine and tan really give us information about the relationship between lengths and angles in a right angle triangle. So if we have a right angle triangle, let's look at example 1, where we can see the hypotenuse length is 289 meters. We have an angle extended of 34 degrees, and we're trying to find x. Well, we can use, in this instance, sine theta, so sine 34 equals x over hypotenuse, 289. So with cross multiplication, we can say x must equals 289 times sine 34. We'll take the calculator to calculate that. We'll just cancel what's on the calculator there, and to always check that we've got a D up here, degrees, just in case we had an or there, we'd have to do shift mode, and you can switch from degrees to radians. So 3 is what we want. We're working in degrees, so we'd stay with D, and we have a D up at the top there. So we want to do 289 times sine 34. And that gives us the length of 161.6 meters. Now, if we knew the other angle in this triangle, I'll just switch to this angle here. We could also use this angle if we had cosine. We could use cosine. Cosine is the adjacent over the hypotenuse. The sum of all angles in any triangle is always 180. So we know a right angle triangle is 90. The given angle theta is 34. The 180. So we just call this angle. Just call angle C. So angle at C equals 180 degrees minus 90 plus 34, and that gives me 56 degrees. So I could equally have found my x, my unknown x, by saying cosine of the 56 degrees equals the adjacent, which is now x, because that's beside the angle C, over the hypotenuse, 289, and so x would be equal 289 times cosine 56, and that's just to verify that there's 2 ways to approach this problem. So let's just delete back. So we've 289 times cosine 56 degrees, and that should give us the same answer as 289 times sine 34 degrees. And indeed it does, 1.6160. 161.6 meters. In the next example, we are going to try to find an unknown angle in a right angle triangle where we have the lengths of the right angle triangle. So we can see the hypotenuse is 5, the opposite is 3, and the adjacent is 4. So to find an unknown angle, we are going to use the fact that we have sine. Our unknown angle theta is 3. Opposite over 5. We can use the inverse sine function, inverse sine, to actually free up the angle. So inverse sine. So if we take the inverse sine of both sides, sine minus 1 is the inverse sine of sine theta. That cancels and gives us theta. If we do that on the left, we must do it on the right as well. So theta equals sine minus 1, 3 over 5. And we look at the calculator to see that function. So we are looking at sine, the inverse, shift sine gives us the inverse function, 3 over 5. And close bracket, and that will give us an angle in degrees of 36.869 degrees, so we'll say that's 36.9 degrees. Now we get that, we could also use the fact that cosine theta is 4 over 5. That's the adjacent over the hypotenuse. And likewise, we can do an inverse cosine. So if we do cosine minus 1 of cosine theta, we are left with cosine, because those functions cancel each other. We're left with theta, rather. So inverse cosine, cosine theta, releases the angle theta. So we do that on the left, then we do it on the right as well. So we can use the inverse function to find an unknown angle in the right angle triangle. Let's just check that on the calculator. So we have cosine inverse, so we shift cosine 4 over 5. And that should equal 36.869 degrees, or rounded to 36.9 degrees. So the inverse function is a very useful function. That's all for this video for now. Thank you for watching.